CRAY T3D system is the first of a new generation of supercomputers from CRAY Research, based on the principles of massively parallel processor design. This lecture will describe architectural and hardware implementation aspects of the CRAY T3D. A second tape in this series will describe the system software and application software environments. This new family of supercomputers complements the highly successful line of CRAY parallel vector processing systems. Those products, the most recent of which is the CRAY C90 and its dependents, have roots tracing back to the original CRAY 1. The CRAY 1, a universally accepted guidepost for the industry, was designed by Seymour Cray and introduced in the marketplace in 1976. Significant changes have occurred since those early days at CRAY Research. Most compelling are the great advances in the integrated circuit density and speed. These advances have spawned multiple generations of microprocessors and inexpensive semiconductor memory. In fact, the latest microprocessors now challenge the performance claims of the original CRAY 1, but at a small fraction of the cost. By combining this microprocessor technology with advanced CRAY proprietary integrated circuit, packaging, and cooling technology, the CRAY T3D has been designed to solve highly parallel, very compute and I/O intensive problems. The CRAY T3D is a multi-processor system, scalable up to configurations of 2048 processors. It operates in a heterogeneous parallel vector and massively parallel environment. The CRAY T3D supports a globally addressable, physically distributed memory subsystem. I/O is also scalable via I/O gateways, which support high bandwidth proprietary channels connected to CRAY parallel vector systems and dedicated I/O processors. The configuration supports a high degree of concurrency to achieve high efficiencies from the computational and data motion resources. Scaling options allow varying subsystem configurations across a wide range. These options allow parallel vector production environments to explore the potential of MPP systems. Others, who have optimized MPP applications in hand, will configure their systems with the majority of the resources on the MPP side. Closely coupling the MPP with proven parallel vector technology serves several purposes. Moving MPP technology into the production environment requires a host of operating system services. In the parallel vector environment, CRAY has more than a 10-year development investment in our supercomputer variant of Unix, which we call Unicos. By adding microkernel technology on the MPP side of it, it has been possible to maximize MPP OS functionality and stability and minimize time to market. It is well known that moving applications onto MPP platforms can be a daunting task. The heterogeneous configuration allows an environment in which an application programmer can manage the work in a staged, incremental way. Finally, the closely coupled connection between the parallel vector system and the CRAY T3D allows new opportunities for high-performance computing. There have been recent reports of applications which have portions of code that map best on the MPP, while other portions of the code do better on the parallel vector platform. The end result can be performance which outpaces either component working alone. The CRAY environment will support efficient heterogeneous computing using the parallel virtual machine software technology. PVM was originally developed through a three-way collaborative effort of researchers at Oak Ridge National Laboratory, the University of Tennessee, and Emory University. The CRAY T3D compute and I/O nodes are interconnected with a three-dimensional toroidal switch. The switch is designed for very high bandwidth and extremely low latencies, setting a new standard for massively parallel switch design. The switch supports independent, bidirectional paths to nearest neighbors in each of the 6 directions, which can be thought of as up, down, north, south, east, and west. A 7th pair of paths provides connectivity to the compute resources associated with the node. The switch manages a peak input flux and, of course, an equal output flux of 16.8 gigabits or 2.1 gigabytes per second. Unidirectional switch and wire latency for a 2-byte wide packet fit for physical unit is typically 13.3 nanoseconds. When routing requires a corner turn, there is only an additional 6.7 to 13.3 nanoseconds of delay. What kinds of problems have the potential to capitalize on the computing power delivered by large numbers of processors, numbering in the hundreds or even thousands? While we are interested in delivering a high degree of sustained as opposed to peak performance for real-world applications, the most important objective must be in reducing the time to solution. The problem and selected algorithm must, of course, be highly parallel. As is well known, Amdahl's law observes that for practical problems, the total execution time will consist of a parallel portion parceled out to a collection of processors, plus a serial portion which cannot be performed in a parallel manner. If large numbers of processors are frequently forced to wait for the computation of data coming from a single processor in the system, plus the additional time required to distribute that data, the actual benefit of the large numbers of processors will be reduced. At some point, adding more processors is no longer cost-effective in reducing the time to solution. Even for a problem which is 95% parallel, one cannot expect speed-ups beyond 20, even with an arbitrarily large number of processors. Massively parallel, or MPP systems of hundreds of processors require problems that are more than 99% parallel. The problem design should not only be highly parallel, but it should exhibit high algorithmic efficiency. Each calculation should be effectively moving the problem toward the solution. A high sustained floating point operation rate is diminished in value if the algorithm demands many more intermediate results than a competing algorithmic choice. Third, it must be possible to efficiently move dependent data to requesting processors. This communication overhead can have the same effect as the serial portion of the computation. Here, we are interested in algorithms which require only modest amounts of interprocessor communication, or which allow mechanisms in design to effectively make the latency transparent. This is accomplished by hardware and software prefetching techniques. The importance of each of these criteria, algorithmic efficiency, a high level of parallelism, and moderate or transparent interprocessor communications, can be mitigated by selecting ever higher performing processors and communication networks. But in the real world, users are also concerned about price performance. It would be terrific if we could design a system consisting of 1,000 processors, each with gigaflops of performance, an interprocessor network that delivers tens of gigabytes per second of data flux for each processor, and interprocessor latencies below 100 nanoseconds. The problem today is that such a system, if it could be built, would be outrageously expensive. This will no doubt be less true tomorrow. Today, however, we are faced with a series of important architectural and technology trade-offs. Properly made, there is vast potential for improving the price performance of challenging and grand challenging problems having the characteristics just described. The rest of the story, then, will take you through the series of architectural and technology choices and trade-offs made by the designers of the CRAY T3D. Three distinct kinds of parallel programming models and the accompanying high-level language constructs to support them have evolved. These models are data parallel, message passing, and work sharing. Data parallel models use a limited, often single control flow within the system to control a very large data set. Data communication is usually specified implicitly in the high-level language, using, for example, naming which references entire arrays of data. Interaction among individual data elements is masked by high-level operators such as matrix multiply, transpose, or inversion. Message passing models recognize distinct data domains, which may represent real domains in the problem space or which may just be artifacts of the organization of the computer system itself. In any case, explicit communication sequences are specified, indeed required, which serve to move data and also provide a low-level synchronization function. The third model is work sharing. The emphasis here is on implicit data motion requests automatically invoked by the use of variables representing a fine degree of granularity. The naming can effectively specify and use arrays, array elements, and scalars. Multiple control flows are supported through a rich set of synchronization primitives. The objective here is to keep a high percentage of the processing cycles actively performing real work. Without applications, particularly third-party applications, no supercomputing system can be broadly successful in the marketplace. Although application development remains in an immature state, the variety of applications which do exist and which must be supported for market success use all three models: data parallel, message passing, and the emerging work-sharing model. The CRAY T3D was designed to efficiently support all three. Let's turn our attention to the variety of architectural and implementation choices for massively parallel processor design. It is expected that for highly parallel problems, significant performance gains will come from large numbers of processors working together. But there are two distinct ways this cooperation might be enforced. The collection of processors could follow the single instruction multiple data, or SIMD model, or the multiple instruction multiple data model, the MIMD model. In the first case, each processor operates in lockstep with all other processors in the partition, but with different parallel data sets. In the second case, MIMD, each processor follows its own control flow, executing from a distinctly different instruction stream. SIMD designs are a good match for data parallel models and can be somewhat simpler to program. On the other hand, they suffer from inefficiencies when, for example, sparse matrix data is being manipulated in rather naive ways with lots of multiplications or additions of zero operands. Although the operation count may be high, the algorithmic efficiency for this example is low. MIMD systems provide many more degrees of freedom, with conceptually each processor operating from distinctly different optimized control stores. In practice, however, the computation would probably be broken up into a handful of computational domains. There may, for example, be separate code to simulate a physical structure's interior and separately its boundary regions. Whereas synchronization is implicit for the SIMD model, with all parallel calculations occurring simultaneously, it is necessary for the MIMD case to manage more explicitly the limited interaction among processors. This adds to complexity at the application programmer, or at least the compiler designer level. Nevertheless, the opportunity for high real performance has caused almost every MPP vendor to concentrate on MIMD designs. And the CRAY approach is no different. The CRAY T3D is a multiple instruction, multiple data design. The next important choice involves the way in which memory and ultimately data is shared among processors. Parallel vector systems from CRAY Research and others use a uniform access, physically shared memory implementation. With this approach, the processors and the memory subsystem form two distinct and physically separated resource pools. All processors compete more or less equally for access to each location in the memory subsystem. The latency each processor sees is also approximately equivalent. Although not fundamental to the physically shared design, the communication paths between the processor partition and the memory partition are often highly optimized for high bandwidth and low latency, adding significantly to the supercomputer system cost. Unfortunately, such system organizations do not scale well to large numbers of processors because the required number of independent data paths grows exponentially. The non-uniform physically distributed memory model provides a much more scalable solution with each processor located physically nearby a set of memory devices. The processors can then have preferential access, that is, lower latency and/or higher bandwidth, to the nearby memory. The non-uniform memory access model can provide a much more cost-effective solution for parallel algorithms that emphasize a high degree of local computation and only moderate amounts of global data movement. Whereas the high degree of connectivity in the uniform access memory system may be underutilized a significant part of the time. The CRAY T3D utilizes the non-uniform physically distributed memory model in its construction. However, through its memory addressing mechanism, it, in a logical sense, preserves the concept of memory sharing, allowing the CRAY T3D to operate as a true multiprocessor. Many MPP systems to date have been designed as multi-computers, not multiprocessors. Interprocessor communication must depend upon explicit I/O-based requests. Data moving from one processor to another must pass through the I/O ports of the processors. This usually requires the use of processor interrupt mechanisms and even intervention by the operating system. The target processor must decode or interpret via software techniques the address tag and the purpose of the message to determine the exact source or destination for the payload. This results in significant increases in latency for the interprocessor communication process. A multiprocessor, on the other hand, provides direct paths to each memory location within the entire processor pool partition. Addressing is managed through a single global address space. On the target end of the transfer, the data communication mechanism does not interrupt the processor, but proceeds directly via hardware support to that processor's local memory. Because network communication within less efficient multi-computers lacks a unique global addressing mechanism and also requires processor intervention on each side of the transfer, the programming models on these systems are dependent upon the message passing model. For a multiprocessor system, however, a true work-sharing model can be implemented. The specification of data using a high-level language, whether local or global, can be consistent. Memory references, local or global, at the hardware level are direct with very low overhead. It is very important, however, for the CRAY T3D to effectively support message passing, and it does. Explicit message passing send and receive requests are translated to allow, at the lower hardware level, actual data movement to progress through the multiprocessor memory protocols. Let's concentrate now on the interprocessor data communication network to provide motivation for the network topology and switch characteristics selected by the CRAY T3D designers. Access by processors to the local memory on the same node results in preferential treatment with higher bandwidth and lower latency than access to memory locations residing in neighboring nodes. When making trade-offs among resources spent on local versus global traffic, support for locality of data has priority. We have seen that the CRAY T3D is a true multiprocessor. Although processors own local memory resources, that memory appears logically as part of a larger, globally addressed, physically distributed shared memory subsystem. Although the objective in programming for a distributed memory system should always be to maximize the occurrence of local calculations and thereby minimize global traffic, it is nevertheless helpful to minimize, within reason, global latency. We give this priority because a certain amount of global communication for real-world problems is unavoidable. But we want more than low latency. We also want to include mechanisms which allow the system to hide latency whenever possible through invocation of prefetch mechanisms. Network paths should obviously be high bandwidth within the constraints of system cost trade-offs. The CRAY T3D achieves both low latency and high bandwidth by using true supercomputer technology. Microprocessor shell and network switch logic are clocked by a single synchronous 150 MHz clock distribution network. Market requirements for massively parallel systems dictate support for a wide range of system sizes with incremental pricing structures. The network must be scalable with a fairly linear increase in cost to match linear increases in the number of processors. Fault-tolerant features must be considered when designing the switching network. Reconfiguration can allow masking of hardware faults until scheduled maintenance, increasing system availability. Finally, the system architect should be aware of the technology choices which will be available to those who implement the hardware design. Advanced packaging to support high clock rate designs have been a trademark of CRAY research designs through the years. With time to market always an important consideration, it is wise to exploit but not overextend the technology reach of each new product. Good judgment, therefore, requires a good technology fit with the design and manufacturing processes of the organization. And now Steve Oberlin will discuss the details of the interprocessor communication network.
Thanks, Steve. As previously mentioned, CRAY T3D processing elements, or PEs, communicate over a high-speed network configured in a three-dimensional torus topology. What's that? Well, to illustrate, let's start with networks having less than 3 dimensions. This is a diagram of a simple single-dimension torus network connecting 8 nodes. The links between them carry data packets at some maximum rate we're not concerned with for now. There are a few things worth noting about this network. First, what's the latency of the network going to be? Topologically speaking, there are no ends to the network. During random global communications, a packet can choose to travel whichever direction around the network is the shortest path to its destination. The worst case distance, then, is to a node halfway around the network. If we measured latency in hops, the maximum for this network would be 4 hops. If you look at all possible communications between PEs, the average latency is about 2 hops. Second, what is the bandwidth of this network? The ability of the network to carry global traffic is measured by counting the number of wires that would be cut if you snip the network in 2 at the center. This is called bisecting the network. When you multiply the result by the speed data moves on each wire, you get a metric called the bisection bandwidth. And for this simple 1D example, the bisection is 2 times the channel rate. In this diagram, it looks as though the link connecting the ends to form a torus must be a pretty long wire. In reality, it's possible to fold a torus so that all wires are about the same length. This diagram is also a torus, and it's topologically equivalent to the previous diagram, only the wires go from node to node in an interleaved pattern. In T3D, 2 of the 3 dimensions are folded in this fashion. There's one other characteristic of the torus that's worth mentioning. It's naturally fault tolerant. Suppose one of the links broke for some reason. The torus provides a second path between nodes, the long way around the network, so that the system can continue running. The more processors in a system, the more important fault tolerance becomes, because the failure of a single PE or link represents a correspondingly smaller fraction of the machine. Who wants to give up their machine for repair if a failure only costs 1,000th of its capability? Let's look at a more complex network, an 8-node 2D torus. Now nodes are connected to their neighbors in 2 dimensions. By adding a second dimension, we double the bisection bandwidth to 4 over the 1D torus. Maximum latency is now 3, and the average is less than 2. These effects are magnified the more nodes you have. For instance, a 64-node torus has 8 times the global bandwidth of a 1D torus and a maximum latency of 8 instead of 32. You can see where this is going by now. By stacking planes of 2D tori and connecting nodes in the 3rd dimension into a torus as well, we can construct a 3D torus, which is the T3D's network topology. We've again doubled the bisection bandwidth to 8, and maximum latency is now 2, and the average barely over 1. Again, the biggest advantages of adding a dimension come with the larger sizes. At 64 nodes, a 3D torus has 16 times the bandwidth of a 1D torus and a maximum latency of 6 instead of 32. For comparison, the largest size T3D has a torus with 1,024 nodes in an 8x16x8 configuration. Data packets route through the T3D network in dimension order. This means that a packet injected into the network routes in the x dimension first, then the y dimension, then z, until it reaches the destination node, where it's ejected from the network. So what does a T3D network node look like? This block diagram shows the communication paths associated with a network switch. Each network node in T3D is shared by 2 independent PEs. The PEs are logically separate and only share the bandwidth of a network switch and a data mover called the block transfer engine, which I'll talk about later. There are high-speed channels radiating from the network switch in 7 directions. 6 of those directions are for the 3D torus connections. The 7th direction is the channel to the PEs. Each channel is actually 2 unidirection channels that operate independently. In other words, it's possible to have data streaming through the switch from east to west at the same time other data is moving from west to east. Packet steering is controlled by a routing tag in the header of a data packet that specifies the number of hops a packet should travel in each direction. In T3D, routing tags are stored in a high-speed lookup table at each node. When a data link fails, the routing directions in the lookup tables are simply changed to avoid the bad link. T3D also provides some extra compute nodes as spares in the event of a PE or node failure for increased fault tolerance. There are 8 redundant PEs for every 512 PEs. Redundant nodes can be electronically switched in place of a failed compute node by rewriting the lookup table to substitute the redundant node for the failed node. The network switch, or router, is actually implemented on 3 chips. Each chip handles one dimension. We call this a dimension-sliced router. Its functioning is fairly straightforward. Packets enter the X dimension switch from a PE and route from X switch to X switch, then turn the corner by crossing to the Y switch chip to travel in the Y dimension, then cross to the Z switch chip for Z dimension routing, then finally emerge at the destination PE. Latency of the switch is very low. Essentially, it takes 1 clock period, 6.7 nanoseconds at 150 megahertz, for a packet entering a chip to decide which way it's going and leave again. At these clock speeds, the time spent on the wires isn't negligible and must also be included in latency calculations. In T3D, all wires are either 1 or 1.5 clocks long. Each hop in the network then takes 1 clock for the switch plus 1 to 1.5 clocks for the wire. Turning the corner is similar to routing within a dimension. It takes 1 clock inside the first chip, 1 clock for the connection between chips, and 1 clock for the second chip, and you're on the wires in the next dimension. Notice this diagram has all the same arrows as the earlier node diagram. Each arrow represents a channel that is 16 bits wide, that is clocked at 150 megahertz for a raw bandwidth of 300 megabytes per second. Earlier we talked about the bisection bandwidth of a network. The bisection bandwidth of a 1K processor T3D, which has 512 network nodes in an 8x8x8 torus, is easy to calculate. The number of channels cut when we bisect the torus is 8 times 8, one plane of the torus, times 2 for the connected ends of the torus, times 2 for the channels in each direction, times 300 megabytes per second, giving a total of 76 gigabytes per second. Data packets carry data in 2 payload sizes, 1 or 4 64-bit words. Packets are broken up into 16-bit chunks called fits for physical units, and sent over the network in a string of successive parcels. The routing tag is always in the first fit, and it opens a path through the switches for the following control and data fits. The head of a packet can easily be many switches ahead of the tail in the network. In scientific literature, this is commonly called wormhole routing. Deadlock is a phenomenon like gridlock in Manhattan at rush hour that can happen when packets in a network are not guaranteed to have room to make forward progress. Deadlock is impossible in T3D because of the use of layers of buffering called virtual channels. By separating the buffering for requests and responses, and providing an additional set of buffers for packets that have passed a certain point in a torus ring, called the dateline, we guarantee network packets can't be blocked indefinitely. T3D thus has 4 sets of virtual channel buffers, 2 for requests and responses before the dateline, and 2 for requests and responses after the dateline. CRAY chose the 3D torus topology after an extensive investigation ending in a final shootout between a couple of champion networks in a detailed simulation using real and synthetic communication patterns. When evaluated within the constraints of real-world packaging limits and wiring capabilities, the 3D torus provided the highest global bandwidth and lowest global latency for the number of processors we expected to have in T3D, hundreds to thousands. Several additional important characteristics include good physical scalability, fault tolerance, ability to exploit locality for reduced latency and improved bandwidth, and a good fit with our technology, that is short wires and a regular wiring pattern, resulting in a high clock speed. There's also significant headroom in the technology that will be used to provide even better network performance in future machines.
Let's define and differentiate 2 levels of the CRAY T3D architecture. These are the macroarchitecture level and the microarchitectural level. The macroarchitecture represents the high-level view of the system seen by the MPP programmer. This includes the globally addressed, physically distributed memory characteristics, in a general sense the topology, which defines relationships among compute nodes, and the synchronization features to the degree they are exposed in high-level language constructs. It is important to present a consistent, although probably slowly evolving, view to the user. This allows generation-to-generation source compatibility. The balance among computational, memory bandwidth, and interconnect support will be also fairly consistent. Application-level optimizations that work well on one generation system should also work well on the next. If a system is successful in the marketplace, this steadiness of purpose will also work to support the development of standards in the MPP world. The microarchitecture roadmap, on the other hand, must be much more agile. Microarchitecture refers to the CPU and the lower-level logic shell, which maps the CPU into the system overall. When beginning an MPP design, one of the first decisions to be made is whether to design a new proprietary microprocessor or to select from a variety of emerging commodity devices. The primary argument for a proprietary design is that it gives an opportunity to specifically and efficiently tailor the microarchitectural design within the context of the overall macroarchitectural goals. But there is a problem. With commodity microprocessor development cycles lasting only 2 years, there is opportunity for rapid improvement, which also can mean rapid change. To be competitive with current state-of-the-art microprocessor designs, which by some counts are already as a class in the middle of the 4th or 5th generation, demands significant design and integrated circuit process development resources. The human resources must be applied in a widely parallel fashion to minimize time to market. There is always an unfolding next generation coming from large competing design groups. For these reasons, even the largest of computer corporations have seen fit to build and support consortia to provide sufficient market presence to pay back the design effort. And of course, these devices benefit from high volume, which allows lower pricing. This counter-argument to embrace an emerging commodity microarchitectural implementation was most persuasive for the CRAY T3D project team. The processor selected was from the Alpha microprocessor family from Digital Equipment Corporation. This device was selected primarily because it best met our objectives of providing high performance and high precision for both floating point and integer data types. We present only a short list of some of the more important characteristics of this device, but would refer you to the other videos in the UVC series featuring lectures by Digital Equipment Corporation engineers. These tapes cover Alpha architecture and implementation in detail. The DEC chip 21064 represents a 0.75 micron CMOS implementation of a full 64-bit reduced instruction set computer. It has a peak floating point performance of 150 million floating point operations per second, utilizing a 150 megahertz clock frequency. Up to 2 instructions can be issued per clock period, or 300 MIPS. The internal register set consists of 32 integer and 32 floating point registers. There are 2 internal caches, 8 K bytes of instruction cache and 8 K bytes of data cache. All candidate commodity microprocessors, including the Alpha microprocessor, were designed primarily to satisfy the requirements of workstations, containing single or at most a handful of CPU devices. This design focus, while appropriate for the workstation market, results in certain weaknesses when it is inserted into a scalable, massively parallel processing system. This is particularly true when the system design has an objective of supporting very large numbers of processors sharing a very large global address space. Fortunately, there are ways in which the microprocessor can be enhanced with appropriate supporting shell logic. A globally addressed memory subsystem designed with the objective of scaling to more than 1,000 processors requires a very large physical address. Even a large workstation memory by today's standards is small compared to that of a fully configured CRAY T3D system. When data cannot be found in the local data cache, the cache miss invokes an external memory reference. Typical microprocessors can support only a very limited number of outstanding memory loads, often only one. But in a distributed memory MPP, any global reference, even nearest neighbor, which stalls the processor, will seriously affect computational efficiency. Logic must be added to support and mask many outstanding references, thereby hiding latency. This provides capability to fully exploit modern compilers that are able to accurately judge when to prefetch streams of data. Interprocessor synchronization must be fast and scalable. Typical RISC microprocessor designs anticipate only very moderate numbers of processors working together within a workstation. Techniques used are often bus-based, such as the popular bus snooping protocol. Due to very real physical constraints, these schemes do not scale well beyond about a dozen processors. Software and I/O-based synchronization protocols used in workstation cluster organizations may scale to large numbers, but fall far short of our goal for providing single microsecond or less global synchronization latency.
The T3D's macroarchitecture can be described by the characteristics that are visible to the programmer. These include the physically distributed memory, which probably represents both the largest challenge and the greatest performance opportunity for a programmer, the global address space, which provides the ability to communicate in a fine-grained manner, fast barrier synchronization, especially useful for data parallel programming, fast memory locks and support for dynamic loop distribution, especially useful for work sharing, and hardware messaging support, especially useful for the message passing programming model. Also visible to the programmer due to their effect on performance are the 3D torus interconnect network, where a programmer may wish to optimize communication patterns or data locality, the block transfer engine, which can help hide remote latency, and the local processor's cache memory, which a programmer may need to be aware of for best performance. Let's take a look at how the PE microarchitecture implements the macroarchitecture in T3D. At the heart of the processing element is the alpha microprocessor. Around the alpha, we've added a shell of external circuits to implement the MPP functions we need. These fall into the three categories Steve mentioned earlier: address extension, latency hiding, and synchronization. The alpha has a 43-bit virtual address space that is translated in the on-chip DTB, that's data translation look-aside buffer, to a 34-bit physical byte address. T3D has up to 64 megabytes of local memory and up to 2K processors, which would require at least 37 bits of address. In reality, this isn't even close. Several additional address bits are also needed to control caching and to facilitate control of the memory map mechanisms that implement the external MPP shell. So, an external address extension mechanism of some sort is required. In T3D, this takes the form of a 32-entry register set called the DTB annex. The way memory is distributed in T3D, addresses have two parts: a PE number part that says essentially which bank of memory, and an offset part that says which memory location within the bank. When the alpha initiates a load or store, the offset portion of the address is taken from the physical address bits that are translated on chip, and the PE number portion is taken from the DTB annex. The choice of which of the 32 annex registers to read for the PE number is made by a 5-bit field above the offset. The DTB annex is readable and writable by user code. The value read from the annex is a virtual PE number, which is translated by a shell mechanism into a logical PE number and checked for validity prior to applying it to the routing tag lookup table to make a remote reference. The virtual to logical PE number translation mechanism is used to create user partitions within the physical torus and provides a good deal of flexibility concerning size and shape of the partition. Shell circuitry always checks the virtual PE number, and if it matches the local PE, performs a local memory reference instead of a remote reference. What about latency hiding? The alpha, like most microprocessors, has a very limited external pipeline capability. When it performs a load, it places the address on its address bus and waits for the data to be delivered before it will move on to the next reference. This may be okay for a desktop system with a single processor when the memory is only inches away, but it's unacceptable in an MPP when the data is at a remote node. We can't have the processor stalled waiting for remote references, so in T3D we've extended the memory pipeline externally by adding a latency hiding mechanism called the prefetch queue. The prefetch queue is a first-in, first-out memory, 16 64-bit words deep, that is used as the temporary destination of remote loads. Prefetches are initiated by executing a fetch instruction, which is an alpha opcode meant to be used as a prefetch hint to a board-level secondary cache. In T3D, a fetch causes a single word load to be initiated from memory, possibly remote, but since the destination is not the processor, the fetch can be acknowledged as soon as we've latched the address, and the processor can continue with other work. When the load response returns, it's placed in a slot in the prefetch queue that was reserved for it at the time the fetch issued. Sometime later, the processor can come back and pop the data from the memory-mapped head of the prefetch queue, thereby hiding the latency of the load. If the processor tries to pop the data from the queue before it's returned, the processor will stall until the data arrives. Using the prefetch queue, up to 16 loads can be outstanding at any time. The prefetch queue is turning out to be a very powerful mechanism easily used by the compiler. Alpha stores to memory do not need to wait for a response, so a large number can naturally be outstanding at any time. This is a good communication mechanism if the producer knows who the next consumer will be, because the alpha has write buffers on board that try to accumulate a cache line, 4 words, of data prior to performing the actual remote store. This increases the payload size and effective bandwidth. A counter in the shell circuitry is incremented each time a store is issued by alpha, and decremented each time a write completes. This counter can be read by the processor at any time to determine when all of the writes have completed for synchronization purposes. The third major latency hiding mechanism is an asynchronous memory-to-memory data mover called the block transfer engine, or BLT. There's one BLT per node, no sense having two since it can saturate the network interface by itself. Once started, it functions independent of the PE, transferring data between remote memory and the local memory in either direction. The BLT can move up to 256K words of memory with a single invocation. The local data that is the source on a write block transfer or the destination on a read block transfer can be addressed with any constant stride. Remote addresses can be any constant stride or can be indirect, meaning the address is from a separate stream previously stored in local memory. Indirect operations are commonly called scatter-gather operations because they can reference data in completely arbitrary ways. The BLT also has a unique mechanism for interpreting the remote address. This mechanism, called the centrifuge, is used to support and control the distribution of data among the PEs that is so critical to attaining good performance on a distributed memory computer. We previously said that memory addresses have two parts, an offset and a PE number. A remote address generated by the BLT must somehow have its bits interpreted to determine which PE to send the reference to and what offset to use once the reference arrives. I've got a couple of examples to show you how this works and why it's so powerful. In a conventional computer with an interleaved memory, an address is usually interpreted as having the memory bank number in the low-order bits with the offset in the high-order bits. If we increment this address repetitively by 1, we see that the resulting address pattern visits the same offset on each bank once, then the carry increments the offset field, and all the banks are visited again. In a distributed memory computer, sometimes the offset is interpreted as lying in the low-order bits of the address, while the bank, or PE number, is in the high-order bits. If we increment this address repetitively by 1, we see that the resulting address pattern traverses all of the memory within the first bank before finally incrementing the bank address to the next bank, where all of its memory is traversed before incrementing the bank again, etc. In our MPP, we'd like to have it both ways. Indeed, we want even more. We'd like to be able to control exactly which bits of the address are interpreted as PE and which are offset. This would allow us to, for example, slide the PE number up by, say, 4 bits so that it had offset bits on either side. If we start incrementing this address by 1, we see that the address pattern touches a block of 16 addresses on one PE before incrementing to the next PE to touch 16 more, and so on. We call this a block distribution. The centrifuge in T3D is controlled by a mask that indicates which bits are PE number. Any place a 1 is set in the mask, the address is interpreted to be a PE number. Any place a 0 is in the mask, the address is interpreted as an offset. The output of the centrifuge is a separated PE number and offset that is used to make a memory reference. Note that bits in the mask do not even need to be contiguous. This permits precise control of the distribution of individual dimensions of multidimensional data arrays. All remote addresses generated by the block transfer engine are centrifuged prior to use. The BLT naturally has a larger startup overhead than direct processor stores or the prefetch queue, so it's most useful when moving larger blocks of data. Now let's talk about synchronization. The PE shell circuitry implements 4 major synchronization mechanisms: barriers, fetch and increment, atomic swap, and messaging. A barrier is a point in a program beyond which no processor should advance before all processors have arrived. Barriers are often used to delineate between parallel sections of code when data produced by the first section is to be consumed during the second section. It is a block form of synchronization that is latency sensitive, since there is usually little to do while waiting for the knowledge that the last processor has arrived at a barrier to be propagated to all processors so that they can proceed. T3D has specialized barrier hardware in the form of 16 parallel logical AND trees that permit multiple barriers to be pipelined and the resource to be partitioned. The barrier resource appears to a PE as a memory-mapped register. When a PE arrives at a barrier, it sets a designated bit in its barrier register to a 1 and waits for it to switch to a 0. When all PEs in a partition have reached the barrier and set the same bit to a 1, the AND function is satisfied and the barrier bits are cleared by hardware, signaling the processors that they may proceed. As an alternative to repetitively testing a set barrier bit to see if it switched to a 0, the processor can enable an interrupt and perform unrelated work until the barrier is satisfied. The barrier has a second mode, called Eureka mode, that supports search-type operations. A Eureka is simply a logical OR instead of an AND. A Eureka is satisfied by any one processor. A Eureka may be used during, say, a database search, where all processors would enable their interrupt on Eureka and proceed with the search until any processor succeeds and terminates the search by satisfying the Eureka. The barrier mechanism in T3D is extremely fast. Even in the largest configuration, it's less than 50 clock periods, about 330 nanoseconds, which is about the latency of a local memory read. A second synchronization mechanism that supports work distribution well is the fetch and increment registers. This set of registers is globally accessible by the PEs. There's 1 per PE. A store to a fetch and increment register acts normally, but a load from one causes the contents to auto-increment. This is very useful for distributing array indices, for example, while strip mining a loop. Each time the fetch and increment register is read, it delivers a value 1 greater than the last. To hide the latency of accesses to the fetch and increment registers, they can be fetched to the prefetch queue. Another fine-grained synchronization mechanism, atomic swap, permits construction of locks in memory or the emulation of full empty bits on individual words of data. The swap is simply an atomic read-write of a global memory location. The value that is stored in the memory location comes from a local memory-mapped register called the swaparand. The value that was originally in the memory location is returned to the PE. The return destination, like any load, can be the prefetch queue in order to hide the latency. Full empty bits in memory are emulated by designating a token value, say an undefined IEEE floating point, not a number or NaN, to mean empty. When a processor wants to load and lock a memory location in order to, for instance, perform an atomic add to that location, it simply swaps the empty token into the memory location. If the return value is also an empty token, then the location was already locked by another PE, and the swap must be retried. If the value returned is a valid number, then the PE has successfully locked the location and may perform its atomic operation. To unlock the location, the PE simply stores the valid data back to memory, overwriting the empty token. Message passing is directly supported by T3D hardware in the form of low-level primitives that permit cache line-sized messages to be sent directly from user space. These short messages are initiated by performing stores through special memory-mapped space to the target PE. The message data is stored in a hardware-managed message queue in the local memory of the target PE, and that PE is interrupted. Hardware automatically allocates space from the sender's message queue in case the destination queue is full and the message rejected. Rejected messages land in the sender's queue and interrupt the sending processor for a retry. Messages carry 32 bytes of payload and are stored in the target message queue with the routing tag and packet control information, bringing the total to 64 bytes per message. The message queue area in local DRAM is 256K bytes, permitting up to 4K messages to be received. The messaging facility is also key to the network error handling mechanism. All network packets have parity on each bit of control information. Data is protected by SecDed. If a parity error or packet misroute is detected when a packet arrives at a node, the entire packet, header and all, is deposited in the apparent destination PE's message queue and an error interrupt issued. That pretty much wraps up our overview of the T3D microarchitecture. Let's step back a minute to discuss the design of T3D's I/O. System I/O is performed via multiple CRAY high-speed channels that connect T3D to a host YMP or to standard CRAY I/O subsystems that contain interfaces to a wide array of peripheral devices and networks. A single CRAY high-speed channel consists of two unidirectional channels, one input and one output, each capable of 200 megabytes per second, coupled with a low-speed control channel that allows the passing of supervisory information. Each high-speed channel pair connects to a specialized node within T3D called a gateway. There are 8 gateways for every 512 processors in a T3D system. Aggregate I/O bandwidth for 512 processors is 3.2 gigabytes per second. Each gateway itself is actually a pair of nodes, each handling one direction of the high-speed channel. The two nodes within a gateway share the low-speed control channel. Each of the two gateway nodes has its own CPU for control, separate local memory, and a dedicated block transfer engine that can move data between memory and the high-speed channel. A gateway node network switch is connected into the network in the X and Z dimensions only, that being all that's necessary to allow complete communication. Gateways are placed on the diagonal of the 3D torus network in order to distribute the I/O bandwidth and minimize I/O traffic contention with compute traffic in the network.
This CRAY T3D processor element module holds 8 microprocessors, 4 on this side and 4 on the back side. Each pair of microprocessors within the compute node is supported by 21 proprietary integrated circuits. These circuits implement high-performance bipolar emitter-coupled logic. Small daughter boards support wide-word dynamic random access memory components. These daughter boards can be easily replaced locally by field service personnel. Each long edge of the motherboard is configured with a dense array of zero insertion force connectors. These connectors provide the high degree of interconnectivity required for the interprocessor channels. The module is liquid-cooled by attaching the circuit boards and integrated circuits to an anodized aluminum cold plate. An inert cooling fluid flows into, through, and then out of the module via hoses connected to a cooling manifold in the chassis. A single CRAY T3D chassis can support up to 512 compute processors, 8 I/O gateways, and additional redundant processors for fault tolerance. The zero insertion force connector is activated and deactivated by inserting a cam down each edge of the module after it has been inserted in the module slot. The cam works to move small sliding contacts one by one out of the chassis-mounted connector half of the mated pair into the half mounted on the module. Bundles of high-performance Teflon wires attached to the chassis connectors provide the toroidal communication paths. The arrangement of the wire bundles can be changed to support the future addition of modules into chassis which were initially configured to smaller sizes. Switching power supplies, each supplying up to 1800 amperes, provide module power. Standard configurations provide for one extra power supply for each required voltage, allowing additional fault coverage for the system. Steve and I have tried to convey our excitement about this design. We believe the CRAY T3D to be a powerful and flexible supercomputing tool. I hope you've enjoyed our presentation. Thank you.